Hi, everyone. My name is Bridget Leonard, and I'm an undergraduate student at the University of Washington, Seattle. This is a pre-recorded presentation for Virtual ICCM 2023. The title of my presentation today is Errors Are the Stepping Stones to Learning. Trial-by-trial modeling reveals overwhelming evidence for mediator retrievals of previous errors in memory consolidation. Errors have previously been viewed as harmful to learning. In standard learning environments, we are often taught to avoid errors. This perspective stems from reinforcement learning, where errors represent an opportunity to reinforce incorrect behavior. However, for more declarative-based learning, such as memorization, errors do not seem to harm learning processes. For example, errors committed with higher confidence are actually more likely to be corrected. This suggests there is some process in which we are able to successfully learn from errors to aid memorization. A common way to investigate error learning or improvements in recall on subsequent fact presentations after an incorrect answer is the pretesting paradigm. During pretesting, participants generate an answer to a prompt before studying the correct answer. Since they have no prior exposure to the correct answer, participants are likely to generate an incorrect response. Although this paradigm encourages errors, pretesting leads to better recall on final tests than studying alone. While the pretesting paradigm commonly involves associated word pairs, research extended its benefit to real-world materials like trivia and educational materials like math problems. Two theories of error learning are commonly referenced in pretesting literature. The elaborative hypothesis states that generating an error related to the cue and target helps form a richer network between them. In a word pair association task, one may generate the error tail in response to the cue whale, when the correct word is swims. An individual could encode a meaningful story with the error, such as a whale using its tail for swimming. At future cue presentations, this elaborative memory will be easier to retrieve due to its grounding in a semantic network. The mediator hypothesis suggests a more episodic account for error learning, in which the error itself is remembered and used as a secondary cue to retrieve the target. In our example, instead of remembering just the word swims in response to the word cue, one could remember their error tail and use it to create an additional retrieval pathway to get to the target. Although these theories are well documented, investigation into the actual mechanisms behind them is sparse. We need a precise implementation of these two theories that reflects real human cognition, pointing us in the direction of ACT-R's declarative knowledge. ACT-R is a popular cognitive architecture that models information processing, memory retrieval, procedural execution, and human performance. Its declarative module encodes each memory in a semantic network. The activation of each memory depends on how recently and frequently you've seen it, or base level activation, and how related it is to the current context or spreading activation. Here we have the activation equation for a memory, or chunk I, that is the sum of the chunk's presentations and their decay based on when you encountered them, plus spreading activation from the current environment, plus some noise that models the noise of a human brain. ACT-R also includes a procedural module which articulates cognitive steps that fire when the states of other modules meet their conditions. To model the elaborative hypothesis within the ACT-R architecture, we use spreading activation. After errors are made and corrective feedback is given, error information is encoded alongside the correct word pair. We see that chunk 4 is more elaborative due to this extra information and attracts more spreading activation than study chunks because it references the cue word twice. And in this way, it's more related to the current context. The mediator method can be modeled by adding an additional production rule that detects errors when they have been retrieved from long-term memory. From the error, it can retrieve the correct target, allowing for a second retrieval pathway other than the typical cue to target pathway. Both these models predict better test accuracy for error items compared to study items, either due to more spreading activation from elaboration or an additional retrieval pathway from mediation. However, these models make opposite predictions for reaction times. In ACT-R, the retrieval time of an item I is based on the activation of I, such that higher activation leads to faster response times depending on the individual parameter K, which accounts for individual differences in retrieval latencies. In elaboration, the activation of an error item E is increased from additional spreading activation so that it is equal to the activation of a study item I plus the extra spreading activation S of E. We can incorporate this into the response time equation. Because the spreading activation of the error item will be greater than 0, the denominator of our equation will be greater than 1 and lead us to have faster response times for error items compared to study items. In mediation, individuals can retrieve an error, then remember it is incorrect, and use it to retrieve the target. Since retrieval time is similar for correct, incorrect, and study items, on the fraction of trials F in which an error is retrieved, the overall response time will be double that of the study item response times. Because F is predicted to occur on at least some of the trials, we can expect the average response times for error items to be longer than study items. To support our models, we collected behavioral data using a pre-testing paradigm in which students memorized 60 weekly related word pairs. In the learning phase, participants learned each word pair once in either an error or study trial. In the error condition, participants generated a response to the keyword that was most often incorrect since word pairs are weakly related and hard to correctly guess. After responding, they were then given time to study the correct word pair. In the study condition, participants studied both the cue and target words simultaneously on the screen. After a distractor to prevent rehearsal, participants took a self-paced final test on all 60 word pairs. To analyze our accuracy, we used mixed linear models to account for individual differences and variability. We fit a mixed model to all experimental trials with condition, error or study, as a fixed effect and a participant level intercept as a random effect to account for individual differences in response accuracies. We also used a binomial distribution to capture the predicted variable, whether someone was correct or incorrect. As seen in this figure, we found a large and significant main effect of condition, such that on average, participants had better accuracy on error items than study items on the final test. The left column in our figure reflects the human behavioral data we collected, and the right shows us our predicted model data, which closely fits the averages. Before running analysis on response times, we cleaned our data to only look at correct responses in a reasonable range to remove various messy data like quick, I don't know responses and long timeouts. We then fit a mixed model with the same fixed and random effects as our accuracy model. We found a large and significant main effect of condition such that on average, participants spend longer responding to error items than study items on a final test. These response time findings support mediation, suggesting that this extra time responding to error items may reflect an additional retrieval pathway. A second mixed linear model was created with a participant level slope as a random effect to examine if individuals are using different strategies like elaboration. This model also found a main significant effect of condition and did not provide a greater fit than the first. Additionally, all the fitted slopes of the model were negative, suggesting that the positive slopes in the figure are due to outlier responses and not the systematic use of the elaborative model. Although our mixed models strongly support error learning through mediation and fit our observed averages well, there's still large variability in this data. Additionally, modeling can capture the cognitive processes of humans better and reveal more insights into exactly how well each model fits each participant. Mixed linear models are by nature unfit to capture the nonlinear dynamics of memory. As we've discussed, ACT-R models human cognition and behavior extremely well. We ran elaborative and mediator ACT-R models using the mechanisms previously discussed to gain greater detail into model fit and individual differences. To do this, we calculated maximum log likelihoods. The likelihood of a model given a vector of data x is the probability of observing the data given the model, or simply the model producing the data. Our data is made up of 60 different test items, so the likelihood of the model given one participant's data is a product of the probability of the model producing each independent response. Since the product becomes vanishingly small, it is common to use log likelihood. In our case, each model was jointly fit to two behavioral measures, the responses x and its corresponding response time rt. To look at log likelihood and calculate it, we have to derive probabilities from the models for both of these measures. Using the Boltzmann equation, we can calculate the retrieval probability of our specific response x, where s is the noise or temperature parameter, and the sum in the denominator reflects all the competing memories for a given cue, like errors and associated concepts from past experiences. To get a realistic representation of the pool of competing memories, all of the responses produced by all participants for a given word were included as a potential distractor in the model and given a trace at time 0.01, resulting in a minimal activation level. In the case of elaboration, this equation was directly applied to the given response. In the case of mediation, a correct response can be made either by retrieving the correct response directly or by first retrieving the error-generated response. Thus, the probability of observing a correct response is given by the probability of the response being correct, or plus the probability of the response being the previously committed error. Using Actar's response time equation, we can compute the probability of observing a given response if the distribution of the noise term S is known. In Actar, declarative memory noise follows a logistic distribution with a mean of 0 and a standard deviation of pi times s divided by the square root of 3. Applying the response time equation to the probability density function of the noise gives us the probability density function of different response times, shown here. To fit the model, we identified parameters for each participant that maximize the log likelihood function using Powell's optimization algorithm. We fit 3 parameters: the decay rate d, which has been shown to vary significantly across people, the noise term s, and non-decision time tr, which accounts for time spent on perceptual and motor processes. W and lambda were kept at a constant value of 1 due to the parameter identifiability problem. W is difficult to separate from D in the activation equation, and lambda has similar effects to TR in the retrieval time equation. To perform trial-by-trial analysis, we implemented the models directly in Python using Actar equations to allow for efficient parameter optimization. In a way that mimicked the behavioral task, for each participant on each trial or test item, the model calculated the probability of retrieving the participant's actual response given the word activations within the model's declarative module, as well as the probability of the participant's response time given word activations and the number of retrievals. The elaborative model assigned higher probabilities to shorter response times on error items due to spreading activation, while the mediator model assigned higher probabilities to longer response times on error items due to multiple retrievals. After fitting parameters and computing the maximum log likelihood for each participant, we found the greatest majority of participants were best fit by the mediator model, with only a few best fit by the elaborative model, seen in our figure. The group level difference in the two models can be computed by aggregating participant level differences. In this case, the cumulative difference in log likelihood between the two models is 1,728. Because of the definition of log likelihood, this difference indicates an odds ratio of e to the power of 1,728, indicating that the mediator model is e to the power of 1,728 more likely to fit the data than the elaborative model. Our analysis strongly supports error learning with overwhelming evidence for mediation. This suggests errors can be used to further optimize learning paradigms, for example, by advocating for pre-study retrievals and recognizing longer response times do not necessarily reflect weaker memories. To fully harness the power of errors in learning, we must identify mechanisms, which we have begun to do through the use of computational models in this study. However, alternative explanations of longer response times must also be examined in this framework to comprehensively understand error learning. We must also understand individual differences, which can be looked at in the scope of computational models of different mechanisms, but might exist more broadly in the fact that some individuals may not learn from errors at all. And finally, we must look at the effect of errors on alternative measures of memory than accuracy. Accuracy is not the most reliable measure, and new research in learning and memory has established more stable and individual-specific parameters, like the speed of forgetting, or how fast a person's memory traces typically decay. Thank you for listening to my presentation today. I would like to thank my advisor, Dr. Andrea Stacco, and my mentor, Holly Haig, as well as our lab CCDL at UW. Thank you.